Hey everyone, welcome back to another video from the Waste Tutor. This video is going to be going over applications of differentiation and applications of derivatives. It's the third of the four final units for this topic. The last one being anti-differentiation, and that'll take us to the end of the Year 11 Methods course, which is quite exciting. So let's move into the unit outline. In terms of applications of derivatives, we're going to be having a look at changes in distance, displacement, velocity, speed, acceleration, and you can see that velocity and acceleration are actually differentiations of different orders to displacement or distance with respect to time, and we'll have a look at differentiating with respect to time as well over the course of this video. We're then going to be having a look at optimization problems, which is where you essentially try to determine where a turning point lies on a function in order to minimize or maximize that function, and we can see that has broad, wide-reaching applications in a variety of fields, and it's very, very useful. Also having a look at more in a theoretical approach in terms of Cartesian representations, being able to determine the slopes of tangents, determining the equations of tangents at specific points along a nonlinear function. And I think that should be it. So let's get straight into the video. Okay, so what I'm going to do in this first slide is I'm going to introduce what the concept of an instantaneous rate of change is, which is something we've kind of already gone over in our first principles approach to introducing how derivatives and differentiation come about. I will then also be having a look at the slope of a tangent and the equation of a tangent given a curve. So when we're looking at our instantaneous rate of change, what I'm going to do first is I'm going to draw my Cartesian plane again with the sort of first principles graph that we've hopefully become a bit more familiar with. And so we've got our y and our x. So we have y here, we have x here, and we consider a curve along this, which we label y equals f of x, so some function of x. And then we can consider some point along that curve p. We can consider some point along that curve q. And what we consider is the equation of this secant, the equation of the line that connects these 2 points. And when we are considering what the derivative of the point P is, it's essentially what happens as Q begins to approach P. So as the point Q gets closer and closer along P, the equation of the gradient, of the secant starts approaching the instantaneous rate of change of P. And so the rate of change, the instantaneous rate of change at the point P is denoted by the limit as Q approaches P. So what does the value of this secant approach as Q comes closer and closer to P? Obviously, the secant doesn't actually exist when Q is directly above P, but we can kind of consider it as a case of it starts approaching a specific value, and that value will be equivalent to the tangent drawn at the point P. So as Q gets closer and closer to P, the gradient of this secant starts approaching the gradient of the tangent drawn at the point P, and thereby it starts approaching the instantaneous rate of change at the point P. And what we were able to do in the previous video on computation of derivatives was we were able to see a rule known as the power rule that we can derive from the first principles approach, which allows us to more easily differentiate a function. And we can also use that power rule to evaluate the value of a derivative, or the instantaneous rate of change of a function at a specific point. So if we take, for example, the case of y equals x squared. So we have a graph here, y equals x squared, and it looks like a parabola, something like this. We have y equals x squared. So if we want to apply the power rule and find the derivative, that is dy dx, so I'm differentiating here with respect to x, and what I'm differentiating is the function y, so that's why I've got the y at the top, d dx of y. And so this is Leibniz's notation that I'm using here. I know that I bring the 2 down, 2, and I subtract 1 from 2, so I get 2x. So my derivative is equal to 2x. Now if I want to find the instantaneous rate of change of y equals x squared at the point x equals 1, that is the point 1, comma 1. 1 squared is 1. So if I want to find the instantaneous rate of change of this function, all I need to do is plug in my value for x into my derivative function, and I will be able to compute what the value of the instantaneous rate of change is there. So in this case, it would be 2 multiplied by 1, which is 2. And so if I was to draw a tangent at the point x equals 1, or the point 1, 1, I know that the gradient of this tangent here would be equal to 2. So I would have something like y equals 2x plus c. Okay? Now, I can also go a step further, and I can calculate what the equation of this tangent actually is. So in the case of y equals x squared, I know that this tangent will be passing through the point 1, comma 1, because it is a tangent at the point 1, 1. And so in order to determine the equation of this tangent, I can essentially just plug in these values 1, 1 into the equation y equals 2x plus c in order to evaluate what the value of my constant c is. So I plug in 1 equals 2 times 1 plus c, and I can see that c is equal to negative 1. And so as a result, my tangent to y equals x squared, which also represents the instantaneous rate of change of the function y equals x squared at the point x equals 1, is y equals 2x minus 1. Now I know I've gone over that relatively quickly. If you need to rewatch what I've kind of said there a couple of times, feel free to do that. And if it still doesn't make sense, make sure you're putting a question in the comment section. So in this way, we've been able to determine the instantaneous rate of change of a function, and we've determined the slope of a tangent. The slope of a tangent is essentially the value of that instantaneous rate of change, and we've also been able to determine the equation of the tangent by substituting the value that the tangent intersects with the function f of x. So in this case it's 1, 1, and in that way we're able to compute what the equation of the tangent is. Now, one of the key applications of differentiation and integration, as we'll see in Year 12 methods and Year 12 specialist, if you go on to do that as well, is that differentiation and integration are really, really helpful in calculating velocity, displacement, acceleration as well. You don't actually formally get introduced to acceleration in the Year 11 course. I'll touch on it briefly. But what it deals with is second order differentiation, that is differentiating your first derivative. So if I differentiate displacement, I get velocity, and if I differentiate again, that is my second order differentiation, I can get to acceleration. And I'll show you how we can sort of get velocity from displacement or speed from distance through differentiation. So generally, when we're talking about rectilinear motion, we generally, in methods, we refer to displacement with an x, we refer to velocity with a v, and we refer to acceleration with an a. Okay? And so we can consider displacement, velocity, and acceleration as functions with respect to time. That is, over time, our displacement changes and our velocity also changes. So we could consider x as a function of t, and this is me using function notation here. And we can say, for example, let's say our velocity is given by the equation t squared plus 3t plus 2, let's say. And then if I differentiate this, I get x dash of t, which is 2t plus 3. Okay? And so if I consider this, this is my derivative of displacement, and more specifically, my derivative of displacement with respect to time. That is, what I'm doing here is I'm taking dx with respect to time, ddt of x with respect to time, and I'm differentiating 2t plus 3. And so what this represents is the rate of change of displacement with respect to time. And so the rate of change of displacement with respect to time, we refer to that as velocity. Okay? So velocity is the rate of change of displacement with respect to time. And so we can equally write this as a function velocity with respect to time is equal to 2t plus 3. If we were to graph this function here, we can consider it as a function like this. We know that time generally only starts at 0, so we won't include anything on this side. So we have x on our y-axis, and we have t on our x-axis, which is a bit confusing, but that's how we would represent it, because it is our displacement that's changing with respect to time, not the other way around. So we have t squared plus 3t plus 2. We know that this will intersect at the point -2 and -1. So I'll just pop that there, and it'll look something like this. But of course, we know that time really only starts at 0. So if we consider this as a more realistic representation of what displacement with respect to time looks like, it would kind of just be like this. Okay, and so that would be our displacement with respect to time, starting when time is equal to 0. So this is our position time graph, and if we were to differentiate this, we would get our velocity versus time graph. But for now, if we consider the tangents of this graph, this function, we would know that velocity is the tangent of this function, or the sort of the slope at any point along this. The slope at any point along this function will tell us the velocity at that time point. So we've constructed and interpreted position time graphs with velocity as the slope of the tangent. We have recognized velocity as the first derivative of displacement with respect to time. Normally, when we're considering position time graphs as well, it won't look like a quadratic function. It might look something like this. We have our displacement increasing. We have a brief stop in displacement, and maybe we start heading back, and then we stop again. Okay, so in this case, we can see that displacement is steadily increasing. We have our x, we have our t. Displacement is steadily increasing, which implies that we have a constant velocity. Okay, this is linear. We have a constant velocity heading up. Suddenly we stop. There's no velocity here. We've just come to a standstill. Now we have a negative velocity as our displacement starts heading back towards 0. And here we have another standstill. We just stop. So our velocity here is 0. At both of these points, we can see the slope of the tangent is equal to 0. So our velocity is equal to 0. Here, our velocity is equal to 0. Here, our velocity is negative. And here, our velocity is positive. And the reason why we know that is because this tangent is positive, the slope of this curve is positive, the slope of this curve is also equally negative in this case. Okay. Another really important branch that calculus helps with is optimization problems. That is, we want to be able to determine where a specific function is maximized and where it's minimized. And more specifically, more generally, I mean, we kind of talk about the global maximum, the global minimum, the local minimum, the local maximum. We talk about extrema of a function. So if we consider a function like this, we have a cubic here. We can consider the local maximum here. This is the point where the gradient is equal to 0. And this is the point where the gradient is also equal to 0. So this is kind of like the local maximum, and this is the local minimum, whereas these kind of extend to negative infinity and positive infinity respectively. But generally, in general terms, this is not what we're really interested in. Let's say, for example, we have a box. Okay, we have a box here, or we kind of have the outlines of a box. And essentially what we want to do is we want to determine what the maximum volume we can get from this box. And so let's say we have a 10 centimeter by 10 centimeter, 10 centimeter by 8 centimeter piece of, a 10 centimeter by 8 centimeter piece of paper, and we want to cut corners out of it, which are of length x. And essentially what we want to do is we want to get the maximum possible volume we can. So this is 10 centimeters, this is 8 centimeters, and we're cutting out squares of x to fold up into a sort of open rectangular box. And what we want to do is we want to maximize the volume. Okay, if we consider the representation of what the volume would kind of look like, we know that it would have a base. This is the base of this rectangular box. Okay, we would have a height x, and we would have a, yeah, that's pretty much all we need. We have this base here multiplied by height. And this base side here is equal to 10 minus 2x on either side. And this one here is represented by 8 minus 2x. Okay? So if we consider the base of this rectangular box, we have 10 minus 2x. We have 8 minus 2x. So that's the area of our base, multiplied by the height, which is given, in this case, by x as we fold it up. So our volume is given by 10 minus 2x multiplied by 8 minus 2x multiplied by x. And if we graph this as a function, it would look something like this. Okay. And essentially what we want to do is we want to find where this volume, the volume of our function, is maximized. Okay. And generally, this will be given by this point right here. Okay? And the way that we can determine where that point lies is the point where our slope of our tangent is equal to 0. Because that's where our turning points occur. That's where our extrema occur. Alright, so if we are to differentiate our volume function with respect to x, we get our function dv dx. And because we use the power rule, the first thing we need to actually do is expand this. So to expanding, we get 80 minus 20x minus 16x plus 4x squared multiplied by x is equal to 80x, take 36x squared plus 4x cubed. Okay? And I'm just going to draw up this graph one more time, just for the sake of making things a bit clearer. Okay, and so if we find our derivative dv dx, we will have to use the power rule now. We get 80, take 72x plus 12x squared. Okay, and now what we want to do is we want to determine where the volume is maximized, right? Okay, so this is our function v with respect to x. And if we want to find the maximized or minimized also, we need to equate our derivative function to be 0, because at the maximum and minimum, our derivative is equal to 0 because it's a stationary turning point. So 80 take 72x plus 12x squared is equal to 0. And if we factorize this, this will yield something like 12, not a great number, but that's okay. 12x plus root 21 on 3 take 3, x take root 21 on 3 plus 3 equals 0. And so in this case, our value for this should be minus 3. Okay, cool. So our value for our maximum and minimum points will be x is equal to 3 plus or minus root 21 on 3. Okay? So the next thing we want to do is we want to determine whether which of these points is our maximum and which of these is our minimum. And the way that we determine whether something is a maximum is by using a sign test. That is, we take a point that is slightly beneath that point, and if it's positive, then we know it's moving up towards the stationary point, and on the other side, it needs to be negative, which means it's moving down away from the stationary point. For minima, it's you have a negative gradient before we reach the stationary point, and we have a positive gradient after the stationary point. We can also have something known as a point of inflection, a horizontal point of inflection. In the case of y equals x cubed, we have a horizontal point of inflection because we have a positive gradient up here, and we have a positive gradient afterwards as well. If we have two positive gradients or two negative gradients, we know that it is a horizontal point of inflection. But right now we're looking for a positive gradient before and a negative gradient after. And so the way that we write up the sign test is we have a table. We have our values for dv dx at the top. we have our values for x. We can consider a point, let's say we have 3, we have -1, we have 3 take root 21 on 3, we have 3, we have 3 plus 21 root 21 on 3, and we can have a point, let's say, let's call it 7. So these are the points that we've chosen, and if we substitute a value for -1 into this equation, all right, we will have a positive value. Here we have 0, here we have 0, we know this. For the value 3, we know we have a negative value, and we have a positive value here. This is something you get by basically plugging it into your equation, but to make things easier and faster, we can also just assume that this is kind of positive. We can see that it's negative, and so we just write positive and negative, and that's enough working to show that we have a maximum or a minimum. And because we have a positive gradient here and a negative gradient here, we can see this is sort of a maximum, and we can see this is negative to 0 to positive, implying a minimum. And so we can see our maximum volume occurs at this point 3 minus root 21 on 3. So our volume is maximized when x is equal to 3 minus root 21 over 3. Okay, and so the value of the gradient at this point will be found by substituting this value, 3 take root 21 on 3, into our initial volume function. Okay, in this case, by substituting that value for x back into our original function here, we get v is equal to 52.51. That's to 2 decimal places. And let's say it's in centimeters cubed. And this is the general process that you follow for optimization problems. Okay, obviously in this case I haven't chosen the best numbers, but there'll be some questions that will get you to deal with slightly more difficult numbers like this as well. So just make sure that you're trusting that you're doing the process correctly. And there's a lot of questions in Sadler, there's also a lot of questions in OT Lee that you can practice as well. So we've kind of looked at solving optimization problems there with sketching curves associated with simple polynomials, determining stationary points and local and global maxima and minima. Kind of with this cubic function that we've got here, we can see that as x tends towards positive infinity, we can have that tending towards positive infinity, negative infinity. However, if we've got an x tending towards positive infinity, we can see that volume seems to be getting maximized here, right? We've got volume tending towards infinity as x tends towards infinity. But the reason why that's not applicable in a real world scenario is because as x tends to infinity, these two terms start tending towards negative infinity, right? And you can't have a side of a rectangular box that is equal to negative, that has a negative length. Okay, that doesn't make sense. And so that's why it's generally the stationary points that we are concerned with in the context of optimization problems, in the context of real-world optimization problems. Okay, there are some scenarios where you could be dealing with these sort of tail ends, for example, when the bounds are maybe restricted, and in those cases it could be possible that the maximum volume or the minimum volume actually occurs at like a point here or a point here, but generally we have our maximum occurring at the local maximum and we have a minimum occurring at the local minimum, the stationary point. Okay. All right, sketching curves associated with simple polynomials, we're able to do that. There will also be some questions where maybe you're given some information regarding derivatives, or you're given some information regarding specific points that the curve passes through, and you'll need to be able to sketch that curve. And there are plenty of questions in Sadler and Nelson that will allow you to practice that. If you have any questions about that, you can also leave a comment in a question in the comment section below this video. Okay, now I know this video has been quite a long one. I've covered quite a bit of content quite quickly, so make sure that if you have any questions whatsoever regarding any of the content that I've covered in this video, that you're asking that, and I will upload supplementary content to explain what's sort of going on. Okay, cool. Thank you for watching this video, and stay tuned for the next one. Thank you, guys.